Mathematics is more than just solving equations. It's about discovering patterns, modeling real world applications, and thinking like a scientist or engineer. Today, we take a closer look at the Fibonacci sequence, its geometric growth, and the secrets it holds in nature and technology. We begin with the simplest operation, addition. But this book, we take addition beyond the classroom. Watch how Fibonacci numbers build upon each other to form a rectangle. I am Anil Kumar. Welcome to my series. And now let's explore the Fibonacci sequence with the help of these four examples. In the very first part, as you know, Fibonacci sequences 1, 1, 2, 3, 5, 8, 13, and so on. It builds on the previous two. You can add the previous two numbers to get the next. 1 plus 1 is 2. And then when you add 1 and 2, you get 3. Adding 2 and 3 gives you 5. 3 plus 5 is 8. 5 plus 8 is 13. And so on. So this next number will be what? The next number will be 8 plus 13, which is equal to 21. So that will be our next number, and that is how it grows. What am I going to do in this particular video is to show you how do we represent the Fibonacci sequence in a rectangle. The solution is already given to you on the right hand side. But we are going to make it so that you understand how you can make it as a project. Then we will show that the ratio of the sides is a golden ratio, which will be approximately 1.6. If we extend this pattern, you can see it approaches 1.618. Then we will draw a logarithmic spiral over the rectangle. Finally, provide examples from the nature with this particular pattern. So now let's begin. How do we represent the Fibonacci sequence in a rectangle? You see, I have a graph paper here. So what we'll do is that we'll make squares with the Fibonacci sequence 1, 1, 2, and so on. So let's begin from somewhere in this graph paper. So let's choose, let's say this square. I'm coloring this as the first one. Okay. So that's my one. And the next square, let's choose another color here. So the next square is also 1, so I'm placing this here. So I'm coloring the squares, each side of which is same as the Fibonacci sequence number. So now 1 plus 1 is 2, so we'll take up the next one, which is a square where each side is 2 units. So that becomes this square. As you can see, the square has sides of 2 units, length and width. Now once you place 1, 1 and 2, you can see a rectangle being formed, and the rectangle dimensions, as you can see, is 3 by 2. Now we need to represent the third one, so I'm using another color here to shade the third one. So we need to place a square 3 by 3 next to what we have. So we are now moving counterclockwise and keeping them together, at least one of the edge. So that square can be colored, which is 3 by 3. Make sense? Correct. So now we have a rectangle whose dimensions are 3 by 5. You can see that. So 3 by 5 are the dimension, and 5 is also the next number in our Fibonacci sequence. Do you see that? So one side is 5 units. So this becomes 5 units. The other one is 5 plus 3, 8, right? So a square of 5 units means 1, 2, 3, 4, 5, right? So we'll color all this. Isn't it very interesting? So it could be a very beautiful project for our students following the book, Crack the Numbers. Crack the Numbers is not just a simple addition subtraction thing, it is how do we apply our learnings and model real life situations. See this interesting Fibonacci sequence. We are just working on one operation, which is addition, adding the previous two to get the next. That's the pattern rule. And what do we get? We get a rectangle, very beautifully looking rectangle, whose dimensions now are 8 by 5. And you can see 8 is the next number in our Fibonacci sequence. Makes sense, right? So, so 8, we need to place a rectangle, we need to place a square 8 by 8 and form another rectangle. Correct. So we already have this side of 8, right? 1, 2, 3, 4, 5, 6, 7, 8. We need 8 on the other side. So 1, 2, 3, 4, 5, 6, 7, 8. So that forms the square 8 by 8. Makes sense? See how easy it is. So systematically, you can move in this particular direction. Keep coloring, right? You must be enjoying this exercise. Do it along with me, right? That is all this book is all about. So it is a book which will enjoy working with. So we just don't teach you basic operations, we teach you much beyond that with very interesting STEM projects. So this is one of our STEM project, correct? So you see, we have colored this one and we have a square. Perfect. So now you see, when we add this 8 by 8 square, what do we get? We get a rectangle whose dimensions are, so on this side we have 13 units. Do you see this? 8 and 5, right? So we have, and on the other side we have 8 units. Make sense? So we have formed a very beautiful rectangle which is 8 by 13. So you can continue this process, and the next will be having a dimensions of 13 by what? 8 plus 13 is 21. So you can continue this process. So that is the first part, to understand that we can actually form very beautiful rectangles using squares. So what did we do? We began with one square, right? So that is our square number one, and then the second one, which is also one unit. And then this is our term number three, which is a square 2 by 2. And then this is term number 4, term number 5, and 6. We kind of moved in counterclockwise, keeping an edge common with the previous one, forming a rectangle. Now, do one more exercise, that is to say, let's say we divide 21 by 13, right? Use calculator and see what do we get. And also divide 13 by 8 and see what do we get. Well, we will also divide 8 by 5 just to see what we are approaching at, right? So let me divide this and write down the values. So 21 divided by 13 gives us a value in decimals 1.615. 13 divided by 8 gives us a value which is 1.625. And 8 divided by 5 gives us a value which is 1.6, right? So you see, all of them have something in common, and that is definitely it is 1.6. And if you continue this process with two more rectangles, you will approach a ratio which is called the golden ratio. So it is 1.618, right? So you can see from 1.6, we kind of approach to this ratio. So 1.6 also is a very close number. As we continue adding squares, the ratio of length to width gets closer and closer to 1.618, known as the golden ratio, phi. This ratio appears in art, architecture, nature, and even in the human body. Now that we have built the rectangle, let's bring it to life by drawing the famous logarithmic spirals. Many of the things have a spiral type of a shape as they grow. So, how do we get that spiral from this rectangle is also another part of this exercise which we are going to do just now. Correct? So, let us build the spiral, and once we build the spiral, we will explore so many examples in nature where you see the spiral pattern. I think already thoughts must have started coming to your mind, things around you with this shape. Your visiting card, for example, is of this particular shape, always the ratio being the golden ratio. Now, let us see step by step how do we build on the spiral. So spiral is a curved surf line, right? So we need a center and an arc. So let's begin with the first two numbers, which is 1, 1. So in 1, 1, what we are going to do is we are going to mark the center as the point being shown here, right? So I have taken a center at this particular point, starting with our first two squares, right? And then we make an arc cutting across this particular area of two squares. So it goes kind of like shown here. Now, to draw the next arc, we will mark the center at the corner of 2 by 2 square, the third one in this particular case, and connect with an arc with this as the center. So it goes kind of like this. You see that. Now, to make continue this pattern of spiral, we'll take the next center at the corner of 3 by 3 square and connect these two. You see that in this particular fashion, you see how this arc is growing, correct? So you can do it beautifully, take your own time to do it, and then you see that. The next one, you can tell me, where will the center be? Well, of course, it will be in the next square, which is 5 by 5 corner, right? So right hand corner at the bottom is one which we use. Sorry, not this one, but this will be right hand top corner in this case. Because we have to go across this, right? So when you connect with this, you can form this particular spiral as going along with this arc, correct? So this becomes your arc, correct? So let's connect all these points and you get your spiral, right? Now the last one for you. Again, we move on so that we have to go across the next square 8 by 8. So taking a center right there and then making the arc from corner to corner, continuing with our spiral. With a steady hand, you can actually draw much better than what I could do. Right. Anyway, but you do see that we have a something like a spiral, right? As you see in many seashells, right? Many animals in this shape. You see that? A pattern which grows in this particular fashion. And if you continue, the spiral grows. That is the logarithmic spiral. In one of our videos, we'll also discuss what is logarithmic spiral. Why in nature do we have it? Those are higher level questions which will be dealt with almost at the end of this book when we talk about logarithmic and exponential growth of things in nature. Everything grows proportionally, but in a logarithmic way. Where the radius is increasing, do you see that? Radius is increasing. So that's the part which I wanted to tell you here. And now I think you can connect many things. First is the golden ratio, which is 1.6 in the triangle formed in this way. And the second is if you consider the area, right, then the area of this particular thing can be shown with the spiral. and that is how things grow. You can see this growth in even in your ears. For example, ram, you see the horns of the ram show you very clearly this particular growth. The seeds of sunflower and many more examples, as you can see in the visuals following now. From the swirls of nautical shells to the arms of galaxies, the Fibonacci spiral is everywhere. Even the way plants grow, their leaves follow Fibonacci angles to maximize sunlight absorption. Why does the spiral appears everywhere? It's all about efficiency and natural growth. The way nature optimizes space, energy, and movement. While you see the whole difference, traditionally, the textbooks teach you what to do, but this book challenges you to think like a scientist and explore like an engineer. From Fibonacci to AI driven mathematics, from number patterns to real world applications, this book is designed for creativity, problem solving, future innovators, and STEM leaders. Crack the numbers for future STEM leaders. Order your copy now. Sharpen your skills and shape the future.